Alright, today is going to be a day of, or this video is going to be for coding up some features of certain papers. These ones are going to be short, so I'm going to do two different papers at once. Usually I'll probably do just one paper at a time. But yeah, these features are short, so it'll be pretty quick. First one is Mixture of Recursions paper by DeepMind. So I'd have you read this paper, come back, and then watch this video to see the code to fully understand what's going on. The second one is Retentive Network. Once again, have you read the paper, come back before finishing. But a quick summary. For Mixture of Recursions, I'm only going to do the recursive part, not the kind of this part, which is the router, which selects only certain tokens to go into the next part of the recursion. I haven't figured out the router part yet, so I'm just going to be showing how you code up just reusing layers, which is pretty simple. And then on the retentive network, I really like this paper. I really like both of these papers. This one is replacing the Softmax function in self-attention. And it looks pretty cool. I guess there is more testing that they need to do to make sure that it's equally as good. Maybe it'll be bad on really long context stuff, context windows. But yeah, let's get into it. We're going to start out with the retentive network. First off, everything we're going to be doing is just adjustments on Karpathy, Andre Karpathy's video of building ChatGPT. The first video, not GPT-2. I have not seen that video yet. I will definitely watch sometime soon. So I have the code here, but we're going to start here to show what's going on. So this first function is going to get basically for each head, we're going to get a different value, which is this. So printed out what you get from this one with 4 heads, 1, 2, 3, 4. Some different values close to 1, but around 0.99, so 0.99 or 0.98. You will take that, feed that into this next function that creates the retention mask. You'll need the sequence length, the gamma, which is each one of these gammas will be fed into each head. Let's go back here, see if we can get a little better show of what's going on. So within the head class, the attention head, you'll take one of these gammas, one of these numbers, and it will be, okay, so you'll create this retention mask, which is this right here. Make sure you cannot look forward in time for each token, just like the, where's it at? Just like this here. You cannot attend to future tokens. If we go back here, see, they do not attend to future tokens. There's only past tokens. So you create this retention mask with a certain gamma. Let's say that one. And then you multiply. So here you multiplied Q and K to get the weights, and then you multiply that with a mask to get this, which you multiply with the V, the value vectors. But okay, so this, for each head, you'll get a certain gamma value, which is each of these. And that is so that you can get kind of different, it allows them to be different, each of the heads to be different, and attend to different things, is what the paper says. So you create one vector of sequence length, another vector of sequence length, going a different dimensions. You compute this distance here, which basically does the n minus m, which is each one of these locations. N is your query, and m, so n is the query, m is so query position, key position. If m is greater than n, which would make distance less than 0, then it's going to set that one to 0 with this right here, this causal mask. Otherwise, it'll do okay, so yeah, that's the causal mask. And then you do the causal mask with the, so you make a bunch of zeros. This starts off as zeros. This D matrix. Causal mask will set these to 0, keep these at 0. And these numbers will be the gamma to the power of distance, as long as distance is positive, of course. And then you return D. So yeah, D starts as a bunch of zeros, and then anything where m is less than n, it will fill in this lower triangle, which is what m less than n will be. It'll fill in with gamma, different gamma for each head, but gamma to the power of distance. That way you get a positional, it gets you a positional encoding. So to the 0th power would be 1, 0.98, let's see, so that's this one, 0.9844, and then 0.9844 squared gets you this one, and then to the 3rd power gets you this one. So it keeps decreasing. Same with all the rest of these, does the same. Yeah, so that gets you this retention mask, which is this D. And then we'll go into the actual code of it. So we have those two same functions will be up here. So you have those functions, and you apply them in the one is in the retention head. So you'll have a gamma will be an extra parameter in your self-attention head. Set self.gamma equals gamma. you will, as normal, do your way equals k times, or q times k transpose. You'll create that D matrix, which will be the retention matrix. And you multiply the way, rather than doing a softmax here, you'll multiply this way with that D matrix and gets rid of the softmax. And then, so if we do need to go up to one other piece of the code that's changed, you do get those gammas here in the multi-head attention, which actually you can get these outside of that for loop. So since this is in the training loop, this would be in the for loop, you could just get this before you do any training at all. So you could do it, let's see. So this is the training loop. You could just do it like right here and then feed that into the heads. Let's see. So yeah, there's that. Multi-head attention. Oh, there is one other thing that this does allow you to do. You can actually get rid of position embedding. So here it would typically be the token embedding plus position embedding, but since the position embedding is actually baked into this, you can actually this was not in the paper as far as I saw, but this is something I added because I noticed there was position encoded into this. You can get rid of the position embedding, which means I can get rid of that and get rid of that. Yeah, so as far as I know, that's not something they did, but that was something extra I tried out, and it seemed to work just as well. But yeah, so that's the retention network. The next part is, let's see here. Okay, yeah, so the next part is just reusing layer. And what you do here is, so first have a recursion depth. I set it to 3. Number of layers equals 3. And what it'll do is it will act like there's 9 layers. It will act like a depth of 9 layers. But yeah, so recursion depth 3, because 3 times 3 is 9. So 3 layers going through 3 times makes 9. And all you do is create your self.blocks one time, and then you feed in the input into, so x is the input, self.blocks of x would be your normal Karpathy transformer. But this one, you feed x into here, into the blocks, makes x, apply the layer norm, and then you just go right back and do it again through this for loop. Takes that, the first iteration's output is x, so becomes the input of the next iteration of the for loop. And that's really all it is. It acts like, so like I said, there's 3 layers, acts like 9 layers, gets you better results than just using 3 layers one time through. And the reason why this one's good is it's parameter sharing. You save a bunch of parameters, bunch of memory. So that's why that one's good. If you were to build it onto a GPU, you can do ways of making it a lot faster. PyTorch isn't the way of making things the fastest. But yeah, like I said, in the actual mixture of recursions, it learns dynamic recursion, and which is basically this picture here, where like first layer through, or first recursion through, all of the tokens go through. But a dynamic router, there's a couple different ways that they talk about, or different ways that they can do this. So all tokens, these dark blue, are the tokens that are going through each layer, or each iteration, each recursion. So all tokens go through the first recursion. Only some go through the second recursion. And then only some of the second recursion go into the third recursion. It just filters out ones that don't need extra processing as it goes through. I'm still working on figuring that part out. But yeah, that is those two. Yeah, this one saves a bunch of memory. Would be faster. It would be much faster if you use the dynamic router. Which hopefully I'll put in a video once I get that figured out better, but I wanted to put this in. The good thing I forgot to talk about the pro of the retention network. First off, get rid of position embeddings, which is my own take. I guess maybe there could be reasons why that would be wrong. It seems to go well with training, but could be other tests to prove otherwise. But the Softmax function is slow. Is a pretty slow thing for training a neural net in GPUs. So get rid of it. This is a faster thing. I mean, it talks about it in this paper. But yeah, that's first video of papers. More to come.